I know you're not talking to me right now.
So let's get started. All right. Shh. So we've been talking about the derivative, right? So when I say the derivative,
Oh, we're just shut down.
Was that a shirtless man?
when I say
Stop talking, Reese.
It's not. He's like, you were not. He's like, it's not.
when I say the derivative, what do you guys think of?
Like taking the derivative of something. It's like it's calculus. Like it's the derivative
What's
of
left
x squared is 2x.
So the instantaneous rate of change, otherwise known as slope. Okay, or you can think of the okay, so these are like equivalent statements. They are all different frameworks to kind of conceptualize this. And depending on the context, you know, one way might be more helpful than the other. But those are all like equivalent statements. In 9.3, we're going to talk about what the derivative can tell us. So we're going to look at what can I learn about f from the derivative. So I can find out where f is increasing by looking at where the derivative is positive. We can find out where f is decreasing by looking at where the derivative is negative. Yeah, I don't know what's going on with this stupid thing, but it's like every time I touch my desk, it just like wants to shut off, which is really stupid. I don't know. It's all like a janky system. This shouldn't be. We should have a hardwired desktop computer where everything works flawlessly, and then I'll take this thing home that I can have something to work with at home. That's fine. But like when I'm in the building, just have like a desktop on every desk that's hardwired into the system that I just log into. And like any room I go into, I just use my login, and there's a computer sitting on a classroom desk. It's like such a simple. Anyways, this is me. So we can find out where f has a local extrema by looking at when f prime changes from negative to positive. That's going to be our local minimum. And then when f prime changes from positive to negative, that'll be our local maximum. We can find out where f is concave down. That's where the second derivative is negative. Or where f is concave up. that's where the second derivative is positive, or where f has an inflection point, that's where f prime changes sign. So it would change from positive to negative or negative to positive. Either one is going to be an inflection point. So these are all examples of things that we can learn about f just by looking at the derivative and kind of how we can go about doing that. Let's do like some computational examples now to just kind of practice doing such. Okay. So it says that given the derivative f prime of x equal to yada yada yada, identify the intervals where the function f is increasing or decreasing. Oh, we're going to use the derivative to do this, right? So again, I know that the derivative is increasing when it's, or the function f is increasing where the derivative is positive, and the function f is decreasing where the derivative is negative. So the only places where a derivative can change sign is when it's equal to 0, or, what's the other or? When else could we change from positive to negative? Where it's undefined, right? Like if you think about an asymptote, you could have something goes like this that's positive and then jumps. Yeah. So if I look at my derivative, what type of function is this?
It's a quadratic.
Quadratic, which is a type of, what's the broader category that quadratics land under? It starts with a P. Polynomial. What do we know about all polynomial functions? They are continuous over their domains. They have no discontinuity. So I don't have to worry about the derivative not existing anywhere because a polynomial exists everywhere for all values of x. It's defined. Everybody good there? So all I have to worry about is where that derivative is equal to 0. So I'll set x squared minus x minus 12 equal to 0. How do I solve something like that? Yeah, factoring seems like a good process here. How does it factor?
It's going to be 4 and x plus
X minus 12, right?
4, x minus 3.
Minus 4 and positive 3. Yep.
Oh, I stuck on something left.
So our solutions are 4 and negative 3. That's why we usually wear shoes, though, so that we can avoid stepping on wet things. Okay, so what I'm going to do now is make a sign diagram. So here's like my number line. Those are the places where the derivative is equal to 0. I'm going to pick a test value from each of those intervals separated by the places where the derivative is equal to 0, and then plug that into the derivative and see whether it is positive or negative. So if I plug negative 5 into this, I'm going to get a negative times a negative,
It's a positive.
which is positive.
Wow. Mathematics.
If I plug 0 in, I'm going to get a negative times a positive.
It's a negative.
And if I plug the 5 in, I'm going to get positive times positive, positive. Now, you could compute the actual values if you want to, but we don't really need them. All we need is the sign. So I usually opt for just identifying where it's positive or negative. So I can say then that f is increasing on the interval from negative infinity to negative 5, or from 5 to positive infinity, because the derivative of f is positive on those intervals. And I can say then that f is decreasing on the interval from negative 3 to 4, because f prime is negative on that interval. Is everybody okay there? Now, alternatively, I could do a similar thing on my calculator. So if I graph that derivative, the function that it gave me, I get this picture. I see that, well, less than negative 3, the graph is positive. Between negative 3 and positive 4, the graph is negative. And after positive 4, the graph is positive, which gives me or I should say, goodness gracious, that should be a 4, right? That's a 3 and that's a 4. Yikes. So that gives me the same information as what I just did with the sine diagram, right? Does this process look familiar, the sine diagram thing? Yeah, it's the same process we used to solve like a polynomial inequality or a rational inequality. You would have done that last year in your pre-calculus course. Okay. Which is nice, right? Like, okay, turns into the same process as before. Super, I'm comfortable with that. Am I doing it a different thing with it? Sure, but if the mechanics are the same and I'm comfortable with the mechanics, like, that's super cool. If I can reprocess or repurpose the same process, that's nice. I already know the process, so. All right. All right. So it says, next example says the rate of change in a population is given by the function dp dt equals 4 over t plus 1, where p is the population in thousands and t is time in years for t greater than or equal to 0. It says to start, find the initial rate of change in the population. When I see rate of change in the population, I know we're talking about the derivative of the population, right? Rate of change means derivative. So when I say here initial, what time is initial?
0.
So all I'm going to be doing then is going to be doing dp dt when t is equal to 0. Everybody's okay with what I did there? Now, this function is in regard to a real-life situation, so it needs a unit. What should the unit for this problem be? For what?
The population in years, population of the years. Thousands per year. Ooh.
Okay. All derivatives are going to be a rate because it's a slope. That rate is going to come from the unit for p over the unit for t, which is years. Does everybody feel okay there? Okay. Part B says, describe how the population changes over time. So to do that, I would start by looking at a graph of the derivative. So gave me the derivative. I'm going to graph that. Now the window I'm going to use x is time. Tells me that t is greater than or equal to 0. So let's make the x min 0. Everybody's okay with that? The y is going to be that change in population. So I'm going to have a positive over a positive. So I know that that y value has to be positive. So let's again make the y min 0 just to get a decent picture, and then let's hit graph. What do you notice about the rate of change in the population? Is it always, think about in terms of what we did earlier, is it always positive or negative, or does it change? It's always positive, right? Well, the rate of change for population could be negative. So since the derivative is always greater than 0, what can I say?
It is always positive.
Increasing. Right? The population's always getting bigger. It's always growing. Never starts decreasing where you lose people. Yeah, it's the rate. That's the rate, not the population. That's the rate. Okay? Now, I noticed that what's happening to that rate as t approaches infinity? And what value is it approaching? 0. So what is that telling me?
It's reaching its carrying capacity. Biological terms.
Yes. Stops. So it's as t goes to infinity, the population stops growing, i.e., it reaches a carrying capacity. That's a great use of vocab. Well, that's why we said approaches. You know. Does everybody feel okay on like how to use a derivative to kind of interpret a real world situation? Okay. All right, let's look at another example.
Where are you at?
Okay. So given the graph of the derivative shown, write down the intervals where y is increasing and where y is decreasing. So the increasing parts are going to be where the derivative is above the x-axis, right? So that's where it's going to be increasing, and it's decreasing where it's below. So y is increasing from A to B, from C to D, and then from, E to positive infinity. Y is decreasing then from negative infinity to A, or B to C, or from D to E. Does that feel good there? E to infinity is increasing. That's okay. Okay. What do you guys think on this so far?
That is
Pretty straightforward.
Everything's logically concluded.
Okay. Moving on to 9.4. we're going to now talk about how we actually compute a derivative. We have not yet done this. Okay. We're only going to have one rule for derivatives. If you were in like an AP class, you'd have a dozen or so. This one is called the power rule. That is something, yeah. So for functions, well, let's say f of x equals ax to the n, so like a power function, the derivative is going to be an times x to the n minus 1. So you just multiply the leading coefficient by the exponent and subtract 1 from the exponent. Nope. Nope. I mean, there's a rule for logarithms that looks a little bit similar to this, but it's yeah, that's exactly right. Okay, so if I have the function 3x to the 5th, what is the derivative going to be?
It's got to be 55 times 5 times the 4th. 15x to the 4th. 15x to the 4th.
Is everybody okay with how we computed 15x to the 4th? I'm going to stop showing the work here in a minute. Is that cool? We're seeing what we're doing. What's the mathematical significance? So if you were in the AP class, we'd show you how to compute the limit by definition, which stinks, or the derivative by definition, which stinks. This is the shortcuts.
That's like,
which is like,
you learned to the definition, and then we learned this afterwards. So
yes,
like, it sucked.
Yeah, it's a problem that takes a sheet of paper to one that you can do in your head. So that's the significance of what we're doing. So what if we have instead like this as our function? How can I do the derivative? You can just do it one piece at a time. So the derivative of 4x cubed is?
12x squared.
Excellent. And the derivative of negative 7x squared is?
14x.
Negative 14x.
Plus 3.
The derivative of 3x is just 3. And then the derivative of negative 5 is 0.
Zilch.
So negative 5 is a constant, right? What's the rate of change for a constant? 0. That's why the derivative is 0.
Take like 1 away from everything? Or what?
So you multiply the exponent to the leading coefficient and subtract 1 from the exponent.
Okay.
So 4 times 3 is the 12, and then I subtract 1 from the exponent, so 3 becomes 2. Okay. All right. What if we have f of x equals 7 over x squared? Great. How do I do that?
Multiply by x squared.
No, I'll just make you...
What is it? Oh, the second rule becomes negative on top.
Very good, Sam. So we're going to use a little bit of algebra to rewrite it this way, so it's in the form that we can use our power rule for derivatives. So that becomes negative 14x to the negative 3, because you subtract 1. And then depending on the directions, if they ask for no negative exponents, then you could rewrite it as negative 14 over x cubed. Does that feel okay? Okay. What if we have 3 times the square root of x to the 5th? You can't just square a function.
Oh, it's to the square something, or what's it called? The negative or the.
Oh, it's a fraction.
Yeah.
And the exponent of an exponent we multiply. And now we're ready to take the derivative. So what is the derivative of 3x to the 5 halves?
15 over 2
X 2 3 over 2. So again, that was. You all get how that works. Speak now or forever hold your peace.
Oh no.
Thanks, the bathroom.
Yeah.
No.
All American action? Mr. Gordon,
You guys got a 2%.
5 over 2 minus 2 over 2.
Yes.
No, the last one. Well, the last one.
Okay. What about this one?
Oh, you do it individually.
Nope.
Oh,
You can reduce it.
It's
an X.
so you were close to
You're close. You want to write it as 2 separate fractions with the same common denominator. Then we can reduce.
6 over x minus x.
X.
Beautiful. That's one.
And we'll rewrite it without the fraction. And now we're in a spot where we can take the derivative.
Nice one.
Yep, you got it.
Ooh, check that.
And if you wanted it without the negative exponent, depending on the directions in the problem, they may ask for no negative exponents or they may not care. So far, so good. What if we have the cube root of x times the quantity x squared minus x?
So it would be x to the 1/3.
Good.
And then you gotta distribute that. And then she said,
Yep.
oh,
Then you want to distribute.
See what I'm talking about?
see, I'd be happy with that.
Yes. Great.
And now you're in a spot where we can apply the property. Now we can take our derivative. Because they're not like terms.
Oh, no. Yeah.
It'd be like taking x squared minus x is x or something, is what you're talking about doing, which is like crazy town, right?
Oh,
They're exponents, not coefficients.
yeah. It's just, it messes with you. Yeah. See where we're going.
I get it. This is why we're doing the practice.
That's good.
All right. That's probably as like all of the tricky things that I could present. If the only rule we have is the power rule, this is like all the tricky ways I could present a problem that you might have to like algebraically rearrange to do the product or the power rule on. But if if all you have is a hammer, every problem is a nail. You know what I mean? That's kind of what's going on here. Let's see. It's okay. I'm gonna grab a couple from the homework and then like one make up my own, and then we're gonna be kind of done for today. Sound good?
What is that? I delivered it.
I know how to do deliverables.
Yeah.
Okay. So find the derivative of y equals 3x squared minus 4x. What's that? Dy dx equals. So that's it. That's the derivative. It says compute the slope of the graph of the function at the indicated points. So the slope is going to be the derivative evaluated when x is equal to 0.
Ooh. Boy, oh boy.
Does that feel pretty easy? Okay. That's just one of the notations we have for derivative. So it just means the derivative of y with respect to x. I want to point something out to you on your graphing calculators. This particular problem, the part 2 of this, computing the derivative at the point, your calculator is capable of doing. If you'd like to see that, I will show you now with your calculator. If you want to follow along, I invite you to take your calculator out to follow along.
Taking out my calculator. I encourage you all to say.
Okay.
Showing followers resistance.
So what I'm going to do is I'm going to start by pressing the math button. I'm going to scroll down to the bottom where I see n derived. That's command 8 on my calculator. So it's putting in the derivative operation for me, that d dx. So I need to fill in the x. And then I'm going to type in my function that I'm taking the derivative of. So that's 3x squared minus 4x. And then we said x is equal to 0. And there it spits out -4 for me. So it's doing the same thing that I'm doing by hand. What your calculator can't do for you is it can't spit out the formula 6x minus 4. But it can check it. Let me show you how to check this. So any of these problems that we did before, that we did by hand, are all checkable. So to check this on your calculator, you're going to start by, I'm going to type in the original function. And I don't actually want to look at the graph of this one, so I'm going to turn off the graphing function on that one by pressing enter on the equal sign so it's not highlighted. And then I'm going to ask the calculator to graph this derivative of this function. To do that, I'm going to press math. I'm going to go to n derive. I'm going to do d dx of the function in y1. So I'm going to put a y1 here. So vars, y vars, function, y1. And then I'm going to do x equals x. So that's going to have the calculator graph the derivative of the function y1. And at the same time, I'm going to graph 6x minus 4. And I'm going to have the calculator graph that with like the thick line. If you have a colored calculator, you don't have to worry about that. But I have the black and white one. And I'm going to hit graph to see if the graph of the derivative from the calculator matches the graph that I just computed by hand. And if they're the same picture, guess what? I know I did it right. So here's the derivative. And here comes the other one. It takes a minute. The derivative takes, and there's the thick line coming in. The exact same picture. Maybe I should have done a zoom standard before to just get the regular XY axis back out there. But, vars over to y vars, function y1. But that makes every single one of these derivatives that I ask you to compute by hand checkable, right? So like, for example, if we weren't sure about our answer for like D, all I would need to do is like, type my function in here. I don't want it to graph, so I'm going to turn that off. And then type my answer here. I can keep this exact same thing, and the calculator will just know what to do. That's the beauty of doing it as like the y1. And if I hit graph again, there's the graph from the derivative. And in a moment here, my answer comes in. Must have. I guess I was just zoomed out too far to tell. But that's the gist of it. So you can use this as a checker. Yes, sir.
How do you, after you put in the derivative, how do you get the other line that is just to compare again? It's supposed to compare the,
So you just type in your answer. And I did it with, oh, that's why it didn't look like it was different. Because I didn't have the thick line option anymore when I cleared the other one out. So if you change the option to like the thick line or a different color, you can tell. So again, like here's going to come in, that's the derivative the calculator did. And then the thicker line that's going to come in here in a second, that's my answer. Notice they're the same picture. So I'm convinced that I have the correct answer. Does that feel good? That's a nice feature. When I was a calculus student, I did not have that option. Let's do a couple more examples from the homework. So it says, find the coordinates of any points on the graph of the function where the slope is equal to the given value. So when I say slope equal to 3, you should think derivative equal to 3.
Yes.
So first thing I'm going to do is compute the derivative. What's the derivative of x squared plus 3x? Okay. And I'm going to set that equal to 3 and solve.
6 plus 3 is 9. Oh, wait.
Subtract 3 from both sides and then divide by 2.
X is, I thought we put X equal.
Okay. So that is the location where on y, where the slope is 3, but it wants the coordinates, right? So coordinates like an x comma y. I know the x is 0. How am I going to get that y? We go back to the original because the original gives you the points on the curve. The derivative tells you about the slope. You can use the derivative to find the x, but to find the y, that you have to go to the original. You know, like f is like x, y's, f prime is like x comma slope. Ooh. Okay, so if you're looking for a coordinate, you need to use f. If you're looking for a slope, you need f prime. Okay. Let's do this example, or this problem from the homework. I like this one because it's it's kind of abstract. So the slope of the curve y equals x squared plus ax plus b, where a and b are real numbers, at the point 2, -4 is -1. Find the value of a and the value of b. When I hear slope of the curve, I think derivative. So if I compute the derivative, that's going to be 2x plus a. Right? The b becomes 0 because it's a constant. And I know that derivative, when I evaluate it at x equals 2 and y equals -4, has to be equal to -1. So if I take my 2x plus a and plug in that x and y, there's no place to put the y, so it doesn't really matter. I get this, and I can solve for a equals -5. Now, am I going to be able to use the derivative to solve for b? No, because is there a b in the derivative at all? No. So what am I going to do? Yeah, I'm going to use the original. I'm going to plug in my answer for a that I've already found. And then this is a point on the original, right? So I get like b is equal to 2. Does that feel okay with what I did there? Okay. I have one final homemade example.
Tangent to the curve fx. Okay, so 3 squared minus 5x plus 1 at x is 1.
Okay. When I want the equation of a line, what do I need? I need two things, right? I need the slope and a point. Yeah. The y-intercept could be the point, or it could be a generic point. Okay. Where is the slope going to come from?
Derivative.
The derivative?
Yes.
Where is the point going to come from?
The function.
The original function.
Yes.
Okay. So, well, let's compute the derivative. So the slope here is going to be the derivative evaluated at 1. And then the point we know is 1 comma something, right? Because of the x equals 1. So the y is going to be just plugging 1 into that guy. So that's going to be -1. So if I use I like to use the point slope equation for a line because I have a point and a slope. And then I can rearrange as directions might indicate whether I wanted a slope-intercept equation or a standard form equation or some other goofy way of representing this. I can just rearrange from there. Does this feel okay? So these last kinds of problems are usually the most challenging because you have to really be careful that you're using f and f prime appropriately to do different parts of the problem. The easiest thing to do is just kind of get lost in the problem and start using f prime when you should be using f, or using f when you should be using f prime. But this is kind of the gist of it. So the way that this is going to work, I'm not going to have a test for Chapter 9 because Chapter 9 and 10, I see no reason that the two should be different chapters. So we'll have a quiz at the end of Chapter 9, and then the Chapter 10 test is going to cover things from 9 and 10. So my quiz description for Chapter 9 should be able to find the derivative of a function using that power rule. Okay? Should be able to find the value of a derivative of a function at a specified value. So like take the derivative and then plug the number in to find. Explain the difference between something like f of 3 and f prime of 3.
Yes.
Write the equation of the line tangent to a curve at a specified x value, just like the example we did just last one, like a second ago. And then use the derivative to find where a function is increasing and decreasing, just like we did to start. That's it. That's the quiz. This should be relatively easy if you're comfortable like doing derivatives and using them. And you have the simplest kind of derivative rule to use, which is wonderful. In the AP Calculus class, you got about 20 derivative rules that you have to memorize.
Is that like, this wants you to do it in different ways?
No, but there's like a different rule if you want to do the derivative of sine, cosine, tangent, sine inverse, sine, cosine inverse, tangent inverse, cosecant, secant, cotangent, inverse sine, or secant, cosecant, tangent. One for logarithms, one for exponentials. Like all these different function groups have their own derivative rule. And then there's rules for like, oh, what if I have a product of two different types of functions? Like the product of an exponential and a trig function, how do I do that? Or the quotient of two different function types, or the composition of two different function types. So there's a bunch of rules that you have to memorize that just are not part of this class. But
Anything else like today?
no, I'm done for today.
An actual purpose
What do you guys think? Now, I gave fifth hour the option of like, when do you want to take this quiz? Do you want to do this on Friday, or do you want to kick the can till after break?
After break.
Friday.
After break.
Well,
Everybody,
After break. Yeah, he's not taking it anyway.
I'm not gonna be here.
So we should wait.
Fifth hour wanted to kick the can till after.
That's,
Yeah.
that's so
I
good.
agree.
Read the original, alright?
Hey, let Henry suffer with us. We do it after.
I see you today. We have time to take it after. We have time. You're not gonna stay for a break.
Yeah, I will. I will lock in. I don't
It's not
know.
like-
Yeah,